All right, last day this week. I don't know about you guys, but I'm ready for like the entire semester to be over, which is abnormal for me. I normally am good for, 7/8 of the semester. And then I get done, but like I'm ready. I'll be rejuvenated by Monday. That's fine. We're doing 5.3 through 5.5 today. And I want to like rewrite where we left off. We had a scenario where there were 18 girls and 12 boys. And if we picked 4 children or people, what is the probability that at least one is a girl? This should be still in your notes. If you don't want to write it again, you don't have to. Remember, we took a look at our options. The options, possible outcomes were 0, 1, 2, 3, and 4. And we mentioned that at least one is a girl is all of these. And we used the complement rule. We said the probability of the complement of the event is the same thing as 1 minus the probability of the event. And the way we use this was the probability that at least one is a girl is equal to 1 minus the probability of 0 girls, which is the complement. And that's where we stopped. Because we didn't really talk about how to decide what the probability of picking 0 girls is when we're picking 4. So we'll show this 2 ways based on the next 2 sections. 5.3 is on independent events. And then in this category, this is in when like we're doing with stuff with cards, and in this case with people, this is where we are replacing the object or person after we draw. In 5.4, it's the without replacement category. So we'll answer this question like we can pick the same girl more than once. Let's answer this like we can pick the same girl more than once. Or 0 girls, so we're aiming for 0 girls, same boy more than once. Let's answer this like we can pick the same boy repeatedly. So with repetition, or with replacement, sorry. After we draw them, we're sending them back out into the room, the audience, we're putting your name back in the hat. When we do this, these are called independent events. If we have 2 or more events going on, and they don't affect the outcome of the others, events are independent. This happens if you put the object back, like with this or a deck of cards. Other scenarios that have this, I'll put that down, like here. Deck of cards with replacement. Rolling multiple dice. Things like that. Even throwing, like, effectively, if you throw 2 dice at once, they can hit each other while they're bouncing, but it doesn't change the probability at the end. For independent events, we have the probability of E and F equals the probability of E times the probability of F. That's the generic way of phrasing it, and we'll walk through how that works in a variety of circumstances. I'm just too tired on weekdays. Like these days I teach when I get home, I don't play fucking video games. Tomorrow morning I'm getting up bright and early, fucking Zelda's popping on. I checked my fucking playtime. Finally looked up how to check my playtime. Over 175 fucking hours already. 175 fucking hours. Over. It said over 175. That's a lot of fucking hours.
Is that the limit?
No, I don't think so. I'll find out. I plan on playing more. Sure, I'll have a fucking 200 cleared before the end of the semester. Because I plan on putting in a good 6 tomorrow and several on Saturday, Sunday as well. They made Zelda, the new Zelda is just so fucking massive. All right, so let's take a look at how to do this, as when you guys tend to write. I'm gonna switch to 2 dice real quick, because I think it's a little bit clearer why or how this is working and why it's working, and then we'll go back to our problem. So like if we roll 2 dice, I'm gonna make a little grid. We'll go 6 across the top. I guess I should have drawn the diagonals of this thing right here. And like say, let's say I've got 1 red die and 1 blue die, so I can tell the difference. And let's say this table is the sum of the 2 dice. Well, if I populate this, takes a little while to write it all in. It goes faster if you notice along a diagonal like this, the numbers are all the same. So all the numbers along this diagonal are 4. All the numbers on this diagonal are 5. All the numbers on this diagonal are 6. Filling this table kind of goes a little bit quicker. Maybe next time I'll fucking print one of these out and just hand it out. That'd be the fucking smart thing to do rather than drawing this by hand like a dumb shit. I'm a dumb shit, you guys are just copying lecture notes. But what does that say about you when you're trying to learn from a dumb shit like me? I don't know. It's a joke for another day. Okay, so like the probability of getting a sum of 2. There's only one outcome that has it, that outcome. The top row and the left column, those are the die rolls. So we don't want to include the top row or the first column. So just everything else in there is that. There's only one outcome that has a sum of 2. And if you count them up, there are 36 outcomes. One, two, three, four, five, 6, and I've got 6 rows, so 6 times 6 is 36. Getting a sum of 2 is saying that the probability that the red die equals a 1 and the blue die equals a 1. And dice rolls are independent. So we can use that formula, and the formula would say that this is the probability that the red equals a 1 times the probability that a blue equals a 1.
So it's only when it's E and F have like the same value?
No, that just happens to be here.
Oh, okay.
I could have said the same thing with the probability that red equals 2 and blue equals 1. That's only going to be one row here. That's going to be this 3 right here. Because the red is 2 and the blue is 1. It's still only 1.
Okay.
Okay. I went with the sum of doing 2 because I knew there's only 1 on the board, but I think your question is a better route to go for explaining stuff. The probability that the red equals 1, there are 6 possible outcomes on the red die. Because remember, probability is the frequency of what we want over the total number of outcomes. So there are 6 outcomes for the red die, and only one of the outcomes is a 1. The same thing is true for the blue dye. There are 6 possible outcomes and only one of them is a 1. We do 1 over 6 times 1 over 6 is the same thing as 1 over 6 times 6, which is 1 over 36, which is what we got up above, the sum of 2. These two were the same. 1 was calculated using that formula. We did the formula right here. Up here, we just looked on the grid and counted how many answers fit the criteria. Let's apply this to the problem with the boys and the girls. Letting Mateo finish writing. I had to blow kisses around him. All right, so back to the boys and girls. We had, what was it? How many girls? How many boys? 18 girls, 12 boys. And we were doing the 1 minus the probability that all are boys. Which means, if I spell it out, that means 1 minus the probability that my first pick is a boy, and my second pick is a boy. Oops. And my third pick is a boy, and my fourth pick is a boy. And that formula we just did with the and going to multiplication, this works with a bunch of ands. So this becomes 1 minus the probability that the first equals a boy times the probability that the second equals a boy times the probability that the third equals a boy times the probability that the fourth equals a boy. I'm gonna know right away whose test is Mateo's. It's gonna be the one I need a fucking magnifying glass to grade. Right?
Probably. I'll go left to right just for you then.
That's okay, I got glasses. All right. How many total kids do we have here? Not in the room, in the problem. 30, we got 30. So the probability that the first one is a boy, there are 12 boys out of 30 students. And then the same thing with the second boy, because if we drew Mateo's name out of the hat, we could put Mateo's name back in the hat, and we got 30 again, 12 out of 30 again. So we could literally pick Mateo 4 times in a row, which is unlikely. And each one of those is 12 over 30. Before I put this in the calculator, I'm gonna reduce this. 12 over 30 is the same thing as 2 over 5. That speeds this up a little bit. Because I know this ends up being 2 times 2 times 2 times 2 on the top, 5 times 5 times 5 times 5 on the bottom. Actually, I can do this without a calculator, all the way up until I get a decimal. 2 times 2 is 4, times 2 is 8, times 2 is 16. And 5 times 5 times 5 times 5 times 5 is 625. Now, at this point, you could probably, well, you probably want to switch to a calculator right here. I'm going to finish her up. This is 625 over 625 minus 16 over 25, which should give me 609 over 625. I think those are going to be the same thing. If I didn't race through my hand math too fast. I'll put it in the calculator like we had up here though, the 12 and the 30, because that's probably where you guys would have stopped. One minus 12 fraction 30 times 12 fraction 30 times 12 fraction 30 times 12 fraction 30. And it's giving me 609 over 625. How do I turn that to a decimal? I just hit the button. That's convenient. As a decimal, this is 0.9744. So this was the probability that at least one is a girl. Did you think we were going to get a number that high? Because what is that in terms of percent? That's 97.44%, right? Almost every single time we pick 4 people out of that group, at least one of them is going to be a girl. Doing this by the other way, doing this the way that we started, we're not going to go all the way because this would take forever. But this is the probability that 1 is a girl, or 2 is a girl, or 3 is a girl, or all 4 are girls. Maybe I don't need the equal sign in there. Get rid of the equal sign. 1 girl, or 2 girls, or 3 girls, or 4 girls. And we saw yesterday that 5.2, the addition rule, or turns into addition. This is the probability of 1 girl, plus the probability of 2 girls, plus the probability of 3 girls, plus the probability of 4 girls. You guys remember when we did the 2 girls one? We wrote out the list of the different options they were. Just the 2 girls alone one, we could have done girl, girl, boy, boy, girl, boy, girl, boy, girl, boy, boy, girl, boy, girl, girl, boy, boy, girl, or boy, boy, girl, girl. And for each one of these little red things between commas, we would have had to do this thing, multiplying 4 fractions for each one of these. That's just for the 2 girls. We would have had to do this 6 times just for 2 girls. then we got doing the 1 girl, then we got doing the 3 girls, then we got doing the 4 girls. You could see how that would get really, really tedious already. Even just talking about it was tedious. Doing it where we just did all boys means we only had to do the fractions once. So you will see problems in the homework that say at least 1. Work smarter. Do the 1 minus the probability of none. This will show up in your homework. Any questions so far? Have you all played Yahtzee? Do you know what Yahtzee is, if you haven't played it? Okay, if you haven't played it, it's actually, you don't even need a box to play it. Like, it comes with a box set, it comes with 5 dice. We'll walk through the probability game. For those of you that have played Yahtzee, you know you don't get a Yahtzee very often. There was one, my wife fucking likes to fucking play it. It's not the most exciting game, you're throwing dice. But she's got, her cousin comes over, her cousin's over today. Her cousin, my wife's disabled, she stays home. So her cousin comes over maybe 2 or 3 times a month on like one of the days. And they play Yahtzee, they play a couple other things, but Yahtzee is one of them. I do sit down if I'm there, like maybe half the time, and I'll play with them once or twice, just so I'm participating with her. One game, I got like fucking 5 Yahtzees. Now, we would play the whole board, there's 6 games on each board. We'd play the whole board, but I got fucking 5. Normally, even if you played the whole board, you're lucky to get 1. It was a fucking crazy day. Let's talk about Yahtzee. Kiara does know. Does anyone else not know what Yahtzee is? It's okay to not know what Yahtzee is. It's a fucking old game. There's no reason for you to know it. So Yahtzee is when you roll 5 dice and you get 5 of a kind. All 5 dice have the same roll.
Okay.
So it's like the probability that we have all 1s or all 2s or all 3s. I put or all 4s. There's a point to this. It's actually a segue to the next section. All 5s or all 6s. Yahtzee, you can pick up the dice that you don't like twice, so you get 3 tosses. We're going to do the probability of getting Yahtzee in 1 throw. So it's a little different. It's a little easier when you can pick the dice up and roll them again. And trying to calculate that is just fucking, I don't even want to do that. Fuck all that. But this is bad enough as it is. So the ors, remember the ors turn into pluses. So instead of writing 1s, I'm going to just say 1s, probably, or instead of writing all, I'm just going to get rid of the all and say this is the same as probability 1s, plus the probability 2s, plus the probability 3s, plus the probability of 4s, plus the probability of 5s, plus the probability of 6s. And each one of these is identical. So I'm not going to show them all, I'll show it once. Let's just look at the probability of getting all 6s. I've got 5 dice, so this is the probability that the first is a 6, and second is a 6, and third is a 6, and fourth is a 6, and fifth equals 6. A lot of writing so far, right? I agree. I think we got all the fucking annoying tedious writing out of the way. I think it's just writing fractions at this point. Well, not quite. Remember the and turns into multiplying? So this is the same thing as the probability the first equals 6 times the probability the second equals 6 times the probability that the third equals 6 times the probability that the fourth equals 6 times the probability that the fifth equals 6. And remember, this is just doing the 6s. It's already fucking tedious. Thankfully, the rest are the same, so once we do one, we don't have to recalculate this shit, we don't need to write it a bunch of times. For each of these, there are 6 possible outcomes on each roll. And there is only 1 6 on each one. And rather than multiplying what that is, well, this is exponent rolls, or 1 over 6 to the 5th. And that's the probability of all 6s. Or all, pick a number.
You actually pick a number?
No.
Oh, okay, let's say.
That's too much pressure. Probably say something like, fuck, it's 7 and I have to slap you. You know there's no slap at 7s on dice. Shit, I'm recording and I just threatened Mateo. Don't show your parents that. I'm waiting for everybody to catch up, because I know I've done a lot of writing here. There's a lot of shit going on. This is probably the most complicated bit of the day. So that's a probability of getting Yahtzees and 6s. We could, if you're curious what that is, if you're curious what this value is, and we're not gonna use it for the next step. That is maybe I should put it down here because it's a lot of zeros. 1286. Not even 1%. Even if I move the decimal by 2 places, I don't have 1%. Is everyone caught up on the writing? So that's what we weren't trying. That's not what we were trying to solve. That was just probability of Yahtzee with 6s. When you're playing Yahtzee, you don't care which number you get a Yahtzee with. So a Yahtzee with 1s is worth the same amount of points as a Yahtzee with 6s. So we're going to do this up here, but each one of these is 1 over 6 to the 5th. I'm not going to rewrite all that shit down. Just know that we got 1 over 6 to the 5th 6 times. Let's get rid of that equal sign right here. What is the equivalent of repeated addition? This is a very common math operation, you guys know. It's multiplication. If I do 2 plus 2 plus 2 plus 2, it's the same thing as 2 times the number of 2's. Same thing here. I have 6 of these, so this is the same thing as 6 times 1 over 6 to the 5th. And if you guys remember your exponent rules, or how the fractions work, that cancels out a little bit and gets us to that. So the probability of any Yahtzee on one toss
Where did the 5 go to a 4?
because I had 1 6 on top and I had 5 6s on bottom.
Oh, so you.
Fraction
cancel
rolls,
out.
1 cancels out.
Okay.
That's worth asking if you didn't recognize. There's a chance someone else didn't recognize what I was doing there. Is that okay though? Canceling out with fractions on top and bottom? Okay. That was fucking tedious as hell, right? There's a fucking smarter way to do this. We're gonna let Support finish writing his thesis paper over here. No, fuck, wait, take as long as you need. We're done with 5.23. That's the idea of 5.3. Well, we're segueing into 5.4. We're in like a transition zone. So I'm not gonna write 5.4 yet, but we're getting there. Where did I lose you?
Is that, I'm looking at the percent.
0.077%. Got a little blurry there, right? I scanned these notes yesterday and I fucking uploaded it. I got it home and I uploaded it. I looked at them. And the way I did it, the scanner, I don't know if you've looked at it. It fucking did it like weird. It's got like this on half of one page and the other half is blank. So I labeled that shit as temp and I'm rescanning them today. And I already tested it on this morning's scans, so I know the correct way to put them in the goddamn scanner. I just brain farted yesterday. It was a long day. Already out of water. I bet you're thirsty, aren't you? You're already thirsty again, aren't you? You want a nice, cold, refreshing drink. Mateo's got one. Keurig got one. Scotland's got icy furnace. I'm gonna take a picture of John Lucas' face. He's got the, you're such an asshole look on his face. Give me 10 minutes, you can go fill it up again, okay?
Oh, that's true, I can wait.
Okay, you guys ready for more?
Yeah.
Is there a smarter way to do this?
Hopefully.
Clearly there is, otherwise I wouldn't be asking, right? So let's think about what happens with the Yahtzee. Let's say I roll one at a time. I roll my first die, and I get a, let's say I get a 3. What is required for me to get a Yahtzee at this point? All the rest of the dice have to be a 3. So, another way to calculate any Yahtzee, the probability of any Yahtzee, is really all that's asking is the probability that the last 4 dice match the first die. And plural of dice is dice, singular of dice is die. That looks like shit. Match the first die. There we go. That looks less like shit. No, it doesn't. Get rid of the word the there, and let's put the down here. Now it doesn't look like shit, other than the scribbles. So, like in the case we said, like the first die equals a 3. This is the probability that the second equals 3 times, since we already know it's multiplication, because these are independent events, third equals 3 times fourth equals 3 times the fifth die equals 3. And each of these is 1/6. And this ends up being 1/6 to the fourth, which is the answer we got on the previous page. You guys ready for more? Yesterday, we talked about the probability of getting a pocket pair. Let's start with pocket rockets, pocket aces. Now, the only way for me to get pocket aces is they both have to be an ace. Right?
Yes.
Ace on the first card and ace on the second card. And we just showed and was multiplication. But this formula right here would be for independent events. If I'm playing poker, are those events independent? No. Poker, these are not independent events. In poker, we don't replace the cards. So this doesn't work. So in 5.4, we're going to look at dependent events. Yeah, we'll have some of it show up a little bit in the next one, but that's a good ending point for 5.3. Do you want to go get more water right now? Does anyone want a break right now? If no one does, I'm gonna keep going. All right. So 5.4, dependent events. And we say they're dependent because when the outcome of one event depends on a different event, on the outcome of another event, we call them dependent events. I'm just going to give a quick example, really easy with dice. What's the probability of rolling a 3? It's 1 out of 6, right? What's the probability of rolling a 3 if you know the outcome is odd? What? It's 1 out of 3. Why? The only odd numbers, there's 1, 2, 3, 4, 5, 6 on the dice, and the only odd numbers on a die are 1, 3, and 5, and 3 is 1 out of those 3 circles. So yes, 1 out of 3. The way we write this last thing symbolically in probability is we do probability of 3, and we put this giant vertical bar, and then we write the requirement, the pre-existing condition. In like letter notation, this is probability of F with the bar E. And the way this is read is the probability of F given E.
What does that even mean? The probability of F given E.
E has already happened. Probability of F given event, probability of event F given or assuming event E has already happened.
So F is going to happen, then E already happened.
Yeah, what is the probability F will happen if E is already a done deal? In this case, we knew the outcome was rolling an odd. We already knew the outcome was odd. Someone told us we couldn't see the die roll, but like someone else could, and they said it's odd. This doesn't happen in real life. No one's gonna tell you it's odd without telling you what it is, but there is a formula for this. There's two versions. One of them sucks. Probability of F given E equals the probability of E and F over the probability of E.
Can't see it.
Thank you. Another way of writing this is or the number of outcomes in E and F over the number of outcomes in E. So as a reminder, the P is the probability version. And N here is counting number of outcomes. So you haven't switched to probability yet. We'll do this odd thing, 3 can be odd both ways. So in terms of the rolling the dice, wait, I need to slow down. I see pencils still moving. More than one. I'm just getting all fancy. It's fucking Thursday. There's Zelda tomorrow. There's Indiana Jones tomorrow. There might be Tony's Pizza. People have been telling, we talked about pizza this morning in the other class, and the first class swore by Tony's Pizza, and I think I've had the pepperoni once, but it's been a long while, and they're like, get chili verde. And I'm like, I really like chili verde, but in my head, that's not a pizza topping. So I'm like, is it good on a pizza? And they said, oh yeah, get it. So maybe chili verde pizzas for tomorrow. Sunday, Saturday, I'm doing paint night at my friend's house. Everyone's gonna be drinking but me, I don't drink anymore. But they have, like, they got a YouTube video, they bought all the paint supplies, it should be fun. And Sunday's D&D. I got some fun shit. Next week's gonna suck. Starting Sunday, I'm going on this potato diet thing. I'll say potato diet for break. Let's look at this rolling on thing real quick. So I'm gonna leave that formula up so you can see it. So like we're working with it. So I said the probability of getting it, rolling a 3 given an odd. Probability of getting a 3 knowing it's odd. I'm fucking this up in my head. What am I doing wrong here? Yeah, that's what I'm fucking at. I got it right in my head, I'm just not going far enough ahead. Okay, so this is the same as the probability of 3 given odd is the same as the probability of 3 and odd over the probability of odd. So for the die roll to be 3 and odd, if it's 3, it's already odd. This top part here is 1 over 6. That's the probability of getting the 3. What's the probability of rolling an odd number?
1 out of 3. It's getting an odd number.
Just on a regular die, not ignore the 3 for now. Just rolling, there's half of them are even, half of them are odd, right?
1 out of 3 is 6.
3 out of 6. Complex fractions, we can, instead of dividing by a fraction, we can multiply by the reciprocal of the denominator. So here we get that 1 over 3 because the 6's cancel. This requires you to remember and work with fractions within fractions. That's exciting stuff. Everybody loves that. Even math guys say, no, I don't want to do that. That's like extra work. So let's look at that number version instead. We want the number of E and F. Now remember here, let's just write it. F is the 3 and E is the odd. So I'm doing N of odd and 3 over the number of odd. On a die, how many outcomes are both the number 3 and odd? Just one, the 3, right? Only the 3 meets that criteria. How many outcomes are odd on a die? 3, the 1, 3, 5. Notice that way we jump straight to the fucking answer. That's the formula for that. That's one of the ways to remember it. So I'll rewrite this here. So ways to remember this. You can either do the whole probability of F given E equals the probability of E and F over the probability of E, or the n number of E and F over the number of E. We wrote that on the other page. Just focusing on the left half, if I multiply through by the probability of E, I get the probability of E and F on one side, and on the other side, I get the probability of E times the probability of F given E. And this is for dependent outcomes. What was the formula for the probability for independent outcomes for E and F? Was the probability of E times the probability of F. And this was independent. I'm gonna put a big fat box around these two because these don't have fractions in them, so they're a little bit easier to remember. My butt hurts.
You want to break?
What?
You want to break?
What?
No.
I need to clean my ears. It's not registering. This is actually kind of neat. This gives us a test for dependence. Well, a test for independence, really. If the probability of F given E equals the probability of F, then E and F are independent. This is more helpful when you know the probabilities. But independence isn't obvious. Let's go back and look at that pocket aces thing. Now that we have a formula for independent events, we can help John Luca, figure out when he finally learns how to play Texas Hold'em rather than 5-card draw. You'll get there. Most people, when they're playing cards like not with family, like in casinos and shit, Hold'em or stud poker is the most common card tables for poker. Let's go back to pocket aces. Probability of pocket aces, which is the probability that the first is an ace and second equals ace. This is like probability of E and F. And so the formula we had for E and F when it was independent was probability of E times probability of F given E. So we're going to line that up with what we have with aces. Probability that both are aces is the same thing as first is ace and second is ace. What we're lining up is E is the first card is an ace. And F is the second is an ace. So if I put this over here, this is like, if I do subscripts, I'll say A1 is like the first getting an ace. Does that work for you guys? Simple notation. Less writing of this first and second bullshit. And this one over here is the probability of the second card being an ace, given the first card is an ace. What?
That's it.
Thank you. Now we just got to do some thinking. What is the probability that the first card is an ace? How many aces do we have in the deck?
4,
We've got 4 aces in the deck, right? How many cards are in the deck?
52.
52. If we have drawn an ace out already, that's what the second is. Probability that the second card is an ace, given that we've already drawn an ace. How many aces are left? I'm gonna write this down so it's a little easier to see later on. How many aces left? And on the bottom is how many cards left? There are 3 aces left, and you've drawn one of the cards, so there's only 51 cards left. So the probability of getting pocket aces is, if you simplify this down, it's 1 over 221. And if we expand on this just for a second, probability of getting any pocket pair. Well, this was specifically aces. So if I want to do any pair, there are 13 different ones of these. There's 13 different outcomes. I can do 1 over 221 on both, or all of them. Is 221 divisible by 7 or 13? It is. This simplifies to 1 over 17. So that's the example of doing like something and then doing the long way of figuring out all the pocket pair. Let's do that Yahtzee reasoning and see if we can get it at 1 over 17 any faster. Because here we had to figure out aces, use the formula, and then apply it to all 13 suits. If we're going for a pocket pair, it doesn't matter what the first card is, right? We don't care so long, well, we do care. Pocket aces are better than pocket twos. But if you just want a pair, you're happy with any pair, doesn't matter what the first card is, it only matters if the second card matches the first card. For that to happen, there are 3 cards left of that rank. There are 51 cards left. It's what we had here. 3 over 51 is 1 over 17. This is taking a while. This is gonna be a long fucking day.
Which one is it?
What?
Is there like a lot to this one?
We got 2 examples that we want to do in this section, because they're not always in this format. Sometimes you have tables and it's like, you want to like know how to do it in a table and stuff like that. Sometimes they have the answers already for you. You got to figure it out based on the probabilities they give you. 5.5 can take a little while. How long is chapter 6? Yeah, chapter 6 takes up a while too. We gotta get it done today. Okay, so let's do an example. A survey was conducted. About faith. And the choices were atheist, God, or some spirit that isn't like the God thing, like a Holy Spirit, but not a God, like some spiritual entity. And they did this over 4 regions. And this is the table that they got for the answers. We had East as a region. We have Midwest. We have South. And we have West. And let's see, we'll put God first. That should appease the religious people in the room, making him a priority. So this is the table of outcomes. And I'll just start writing in the people that did it, the numbers. And the questions we're going to ask What is the probability of someone who lives in the West being an atheist? And we'll switch this around. What is the probability that an atheist lives in the West? So you guys ready to reason this out? This says the probability that someone lives in the West. This sounds like this is a requirement. We're only considering these people. So if we're only considering those people, the idea of the way they're writing this is the probability that someone is an atheist given that they live in the West. If you have the numbers and not the probabilities, you should use the numbers. We should be aiming for probability of F given E equals the number of E and F over the number in E. That's what we're doing right here. We're working smarter, not harder. Oh, I'm off the screen. So this is like my F and my E. So what we want is, if we're following these patterns, we want the number of atheists and West, so atheists that live in the West, divided by the number of people in the West. So it looks like we need information. We need to know the total of this row, right? That's my West row. We need the total of that row. So let's add up how many people live in the West from our survey. And I'm getting 254. How many people were both atheist and West? 26. So they might have you simplify that as a fraction. Or they'll probably just ask you to put it as a decimal. I'm getting 0.1024 to 4 decimal places.
Do we have to convert that to a percentage or not?
If we want to do it as a percentage, that would be 10.24%. I think percentage is something more natural if we were talking to each other and we wanted to know, like that's more meaningful to us. 10%. What the homework is going to ask for, you have to look for it. Sometimes it'll say percentage, and sometimes it actually wants you to type the number and the percent symbol. And sometimes it has the percent symbol next to the entry box, so it just wants the percentage, but doesn't want you to type the percent symbol. And so if you type the percent symbol, it's gonna tell you it's wrong.
Yeah.
It's fucking stupid. All I gotta do is add the right answer with the percent symbol as an accepted response and roll with it. No, they have it programmed to be little bitches is what it is. They're very picky little bitches. Like my old dog. Asher was a picky little bastard son of a bitch. He would only eat a specific type of dog food. And it changed. Which was fucking rude. It would be one type for like a year and a half, and then he'd be like, stop eating it, I'm fucking done with this kind. And then I gotta find something else. All right, let's go on to this one. The probability that an atheist, so we're looking at the people that are atheists. These are my given thing. We're looking at the probability that an atheist lives in the West. We're switching this order around. West given atheist. So this changes a little bit. The top here doesn't change. It's still a number of atheists in West. But now the bottom is going to be number of atheists. And we know the top is still 26. How many does that add up to, though? That all the people in the atheist, we got to figure out how many atheists responded to this survey.
63.
63, I got 63 also. So, if I do 26 divided by 63, I am getting 0.4127 to 4 decimal places, or 41.27%. I don't know how long ago this data was collected. I think the atheist level goes up every year. I think less and less people believe in God every year. I don't know if it's they stopped believing or they were just never indoctrinated in the first place. I've been in both columns. I used to be a believer, now I don't. I attribute that to the Catholic Church. For working for the Catholic Church, they cured me of my religious tendencies. I worked for them for 7 years, so it's like working for them for 7 years as an accountant. They had like, you look like you want to know why.
Yeah.
Even if you don't, I'm going to tell you why. The first Friday of every month, they would have a luncheon. Like the diocese would pay for the luncheon. So this is like the headquarters of the church for like 6 counties. There's not very many of those that work there. There's maybe like 40 people that work there. And the very first Friday that I attend, I'm sitting like next to the lady. She makes fucking dirt look young. She's hella fucking old. I don't remember her name. She was old as fuck. And she worked for the Catholic TV station. And I didn't know her. And she's talking to the person next to her. And I hear her say, I don't know why they won't leave him alone. He said he was sorry to those boys. Now, maybe I took it out of context, because I don't know what the rest of that was talking about. But I know of only one problem that priests have with boys. Some priests are pedophiles, and it gets in the news. That's not something an apology is good enough for. Like, I don't know why they don't leave them alone. I know why. If you were touching little boys and you're a grown man, this isn't fuck appropriate. It's not okay. Apology doesn't cure, fix the trauma you've inflicted on that child. Who's going to live with it for the rest of their life. That was the start of me losing my religion. It was just little things over the rest of the time. All right. You guys ready for the next one in this section? Got one more problem, then we're gonna take a break. Okay? I want to take a break too. I gotta go pee. But I'd rather finish this section and hit pause on the video, stop on the video, make 2 videos. So next one, this time we don't have the numbers, we have the percentages. So in this problem, in 2005, 19.1% of all murder victims. It's already a good topic, right?
I love how random the questions that they use are. Like even in the other stats class that took, it's the most random shit you can think of.
Right?
Makes no sense.
That's nice.
Like, where are you getting these topics?
Right?
Are these real statistics?
I presume.
Okay. Like they're actually taking.
I didn't research it, but I assume that generally they put real shit in the books. In 2005, 19.1% of all murder victims were 20 to 24 years old. Now, I don't know where the region is they're talking about, if this is all the US, if this is a specific city in the US, I'm not sure. So like where this applies to, I don't know. Also, the YO is years old, okay? I don't know what, fuck it. I'll just write years old. Also, 16.6% of all murder victims were male and 20 to 24 years old. Now I'm going to say YO. Now that I've said years old once. So the question here is, what is the probability that a randomly selected (20 to 24-year-old) murder victim was male? Fuck, you're the first one done writing? Did you just say fuck it, I'm not writing it?
Dude, he's like swampy cursive.
No, it's all good, you write what you want. You don't write shit. He's like, I don't even know, he's awake, oh, you heard his name, he's awake now. I know Sarah keeps looking over at you going, is that motherfucker snoring? She didn't say that, she might have not even said MF in her head. That was all me. All right, so what is this really asking? What is the probability that a randomly selected 20 to 24-year-old, this sounds like this is the category of people we're looking at. This is our given criteria. What's the probability that they're male? This is what we want to know. So in terms of our lingo, that is the probability of a male given that they were 20 to 24-year-old victim. Now here, we don't have the numbers, so we gotta use the probabilities that they give us. But this is the probability of both male and 20 to 24 years old from our formula over the probability of 20 to 24-year-old victim. Do we have that information? Let's look. It says in 2005, 19.1% of all murder victims were 20 to 24 years old. Which part of information was that? Top or the bottom? What? Bottom? Looks like the bottom. It doesn't say anything about males. So that's got to be the bottom part. 19.1%. We probably want it as a decimal, so we'll use 1.191. And that says 16.6% of murder victims were male and 20 to 24 years old. So this, the both was the top. This was just the victim itself. And the both top and or victim and male was 16.6% or 0.166. Which means we need to put that up here and that down here. And you will get 0.869 for the probability of a male given 20 to 24-year-old victim. And before we take a break, I want to show you what happens if you get this mixed up. But I want everybody to finish this problem first.
Seems easier to convert percentages into decimals than vice versa.
Really?
I mean, it is.
Percent to decimal than decimal to percent?
Yeah.
You're moving the decimal point 2 times either way.
I don't know, but I feel like it's like more simplified.
Huh. That's an interesting facet of the Teo's brain wiring.
I guess because you don't have to worry about rounding.
That's a possibility.
I have no idea. Whatever the reason, that's what Mateo likes that one. Which way? Like starting with the percent or starting with the, okay. All right, so note. What happens if you have the wrong order? Put them in the wrong spots. Let's say you put the 0.191 on top and the 0.16 on 66 on bottom. You get 1.151 for a probability. Probability of the event is 1.151. One of the first rules there's only 2 rules for probability, and this violates one of them. Probabilities have to be, for any event, it has to be between 0 and 1. This event is greater than 1, which tells me I got something wrong. If you find this happening to you, try flipping your fraction over and seeing if that's the right answer. There's a good chance you just did it upside down. that, I'm gonna stop recording, we'll take a break.